beautiful people, and welcome. In this video, we are talking about graphing exponential functions. Now, this is going to be an introductory video. I am not going to do any heavy examples in this video. We're just talking about what it is to graph exponential functions. We're going to talk about the equation, and then we're going to do examples in part 2 of the video. As always, if I make a mistake, I am human. Please let me know where the mistake occurs so that way we may learn from it together. All right, so we have our general form of the exponential function equation. Here I have y, you can have f of x, it doesn't matter. But we have a, which is the leading coefficient or leading term, times b, which is your base. The exponent is x minus h, both the x and the minus h are in the exponential placement. And then we have our plus k. The first thing that we need to know is the terminology of asymptote. So an asymptote is a line which the graph gets super close to, but it never touches or crosses. It's basically, think of it as like a no touchy zone. We can get super duper close, but we're not actually touching that line, right? It's like annoyingly close, but we're not actually touching that. All right, so let's talk a little bit more about our base. Our base, lowercase b, so here it is, here's our base. If it is greater than 1, so if it is anything greater than 1, we will have exponential growth. That means our function is going to be increasing. When the base is smaller than 1, that means we have exponential decay. That means our function is decreasing. Now, how would that look like on a graph? Now, depending on what your k value, we'll talk about k here in just a little bit, depending on what your k value is, will depend on how your, obviously the function will look like, but where your asymptote, this imaginary line that shall not be touched, is on the graph. But we're going to assume we're doing just regular basic function. So I'm going to write underneath here the parent function, which is kind of like the basic form, and that is y, or f of x, is equal to b to the x. That means there's no h, there's no a, there's no k, it's just basic. All right. So if we have a basic function and the b value is greater than 1, we're going to have an increasing function. So we're going to be going up, exponentially increasing. If we have a decreasing function with a b value of less than 1, that means we will go downward. We will be decreasing. Now notice on both of them, I did not cross the x-axis. So for your exponential functions, you will have what is called an asymptote. An asymptote is, again, that line that shall never be crossed. I'm going to write this as asym. Again, there's no touchy on that line. You touch it, you're going to get, you're going to get injured. No touchy. So because this asymptote here, let me rephrase it, because there is an asymptote here, this value, if we zoom in super duper close, notice that there is a gap between the actual line and my curve. Same thing here, there's a gap between my actual line and my curve. If we were on our phone or on the computer, we can zoom in, keep zooming in, and you'll notice that it doesn't matter what value of x we have, that curve will never get to touching that asymptote. It's just never going to happen. All right, speaking of asymptote, let's go back up here for our asymptote value. So just like we were talking about, transformations earlier on, we have the asymptote. The asymptote is actually your k value. So I'm going to circle this k. Always take the sign with it. This is going to be your asymptote. And your asymptote is that line that shall not be touched. And we're going to call it y equals k. Now this k value, depending on what your asymptote is, will change. And so these green lines here will also change depending on what your asymptote is. Just like we did before in transformations, this is your vertical change. So your asymptote is your vertical change. Your h is your horizontal shift. And then your A, again, tells you your vertical stretch or compression of your curve. All right, let's go ahead and work on asymptote just for a little bit. And so what we're going to have is let's do an example, a quick example. Let's do f of x this time. F of x is equal to 3 times 1/3 to the x power. We're going to say our horizontal shift is 0, so we're not going to have an h, plus 3. Let's do example all threes. So this plus 3 at the end, that's going to be your asymptote. So when it's asking for what your asymptote is, you're going to write y equals 3. This is your asymptote. Now, how would that look like on a graph? 1, 2, 3 on your y, and then you're going to actually show the asymptote by a dotted line. And again, it's a line, so you want to have arrows on both sides because the asymptote is infinite in both directions. Now, it's also invisible, right? It's kind of not there. It's there, but we don't actually see. It's not an actual line. That's why we have it as dotted. Not actually going to graph this. We'll graph this in part 2 of the video, but in part 1, I just want to show you that what the asymptote will look like. All right, let's go ahead and try one more. Let's do f of x is equal to 5 times 7x minus, I don't know, 4, 3, 2, 1. Let's do 1. Again, we're just interested in the asymptote right now. So here it is at -1. So what you're going to do is you're going to find -1. So 1, 2, 3, 4. So here's -1. Dotted line across -1. And that is your asymptote line. Now the equation for the asymptote is y equals this number. Always y equals this number. In this case, y equals -1. And that is your asymptote. So your asymptote, again, tells you where the curve is going to approach. We are never touching this asymptote. We are never crossing this asymptote. So we are either increasing, decreasing towards that asymptote, but we are never actually touching or crossing it. All right, beautiful people, there are 2 more things I'm going to talk about, and then that will wrap up this video. The next thing we want to talk about is end behavior. So there are 2 things that you're going to state. When we're talking about end behavior, we're talking about the behavior of the curve. What happens? That's pretty much what end behavior is what's going on. So you're going to say, as x approaches infinity, y approaches something. So in other words, as x gets bigger, the y values blank, and you have to fill in the blank. So in mathematics, mathematicians are lazy, so I don't want to write all of this. I'm going to use symbols. And the symbols we're going to use are as such. As x approaches infinity, y approaches blank. And the same thing is true as y approaches infinity, comma, x approaches blank. Now, basically what you're going to do is you're going to copy this part and you're going to fill in this part. And again, same thing here, copy this part and you're going to fill in this part. Now let's talk about our last thing, exponential functions for your domain and your range. Okay, so for your domain and range, 2 things are true. The domain, again, are all of your inputs, or in other words, your x values. Your range are all of your outputs and all of your y values. And what's really cool with the domain is that you can choose whatever numbers you want. We are not limited in our domain. We can do whatever we want. Because the number is going into an exponent value, we can choose whatever number we want. If we want 3.75638, cool. We can use that number. Why? Because you chose it. We can choose whatever. And because you can choose whatever number you want, the domain, all of the possible x values are all of the possible x values. So domain, when it's asking you for the domain, it is all real numbers. And sometimes you're going to see it written like this. This is the symbol, all real numbers. If it's real, it can be in the domain. It's not limited. However, that is different for our range. Our range depends on the domain, right? This is our dependent variable. Our independent is the domain, and our dependent is the range. So what does that mean? There is a limit in the domain. I almost forgot how to spell domain for a second. Jeez. So there is a limit on the domain. And what is that limit? The domain, the range. That's why, you guys, I knew I was writing it weird. There is a limit in the range. The domain is without any limits. The range does have a limit, and the range is limited to the asymptote. We are limited to the asymptote. Why are we limited to the asymptote? Because remember, there is a line, an invisible line that shall not be crossed. Can't do it. You cannot touch it, can't do it. That means that my y values stop somewhere. There's no stopping the x values, but our y values stop somewhere. For example, there are no y values here. Like all of this doesn't exist. There are no y values here. It doesn't exist. Why doesn't it exist? Because the curve is not there. So because the curve is not there, that means it doesn't exist on the y, and the y values are the range values, the outputs. So we are limited for the asymptote. So what you're going to do for the range, you're going to write range, and you're going to say y is either less than or greater to the asymptote. So I'm going to say this. Or y is less than asymptote. It's one or the other, depending on, is it above or is it below? Can it be above? Can it be below? We are writing what it can be. For the domain, you're just writing all real numbers. So if it's asking for your domain and range, this is what you're writing. The domain is all real numbers for exponential functions. For the range, you're writing this. Either y is greater than the asymptote or y is less than the asymptote. You are not writing both. You are choosing which one to write depending on your function. All right, beautiful people, that's all the information you need. Please rewatch the video if you need to. In the part 2, we are going to focus strictly on examples. Thank you.